We've looked at experimental probability where we were actually just testing things out and seeing what happens, but more appropriate and often easier to work with and more accurate tends to be the theoretical probability. And so that is actually calculated by analyzing all the possible outcomes and knowing some information. So if we work with that, what we have is a very similar setup. The probability of an event happening is the number of times or the number of ways that event can occur divided by the sample space, which is made up of all the possible outcomes. So all the outcomes that are possible is known as a sample space. So to visualize that, we're going to use a Venn diagram. And you've probably seen these before. There may be multiple circles in them overlapping. We'll look at those in later sections. But a Venn diagram allows us to visualize it. So what happens is that the box contains the entire sample. All the different possible outcomes fit inside this box. And inside the circle, it would be each circle would house an individual event that we want to occur. So in our example here, what we're doing is we have the hearts are separated from a deck of cards, and the probability of drawing a face card from the set can be visualized as what follows here. So I've listed all the cards here. So the sample space, that set, and that set is actually written in these curly brackets. Okay, so sets are written in curly brackets. Curly brackets have the little curl on them, or they might also look like this with a little point on the end, but they are actually named curly brackets. So curly brackets house sets. So we have all the cards in the hearts. So there'll be an ace of hearts, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king of hearts. So those are all the hearts. That's what's inside here. But we're sectioning off the event of a face card. So our face cards are the event we want. So the event of drawing a face card, we can have a jack, a queen, or a king. And then the rest of the cards would be outside of that event. The ace, the 2, the 3, the 4, the 5, the 6, the 7, 8, 9, and 10. All floating around outside there. So our sample space contains all the cards. Jack, queen, and king are part of the sample space, but they're sectioned off because they are the event that we are looking for. All right, now, understanding a little bit about our sample spaces and that, some other methods of illustrating things. We're going to look at the theoretical probability of buying food at a food truck. So what we have is a food truck with 2 mains and 3 sides, and we're going to, for our purposes, assume that you buy a main and a side. You can't just buy one or the other. You have to buy both. So you buy 1 main, 1 side. That's what you get. So their mains are burger and veggie burger, and then the sides are fries, rings, and a salad. So if an order consists of a main and a side, show the sample space using a tree diagram and set notation. So we've already looked at set notation, but let's make a tree diagram here. So what we do with the tree diagram is we kind of look at each item in each level. So our first choice is a main. That's our first level, and then we'll see what branches off of those. So we start with we can buy a burger, or we can buy a veggie burger. And I'm just going to put burger and veggie just to shorten it up here. So we got a burger or a veggie burger, and there's our first branch off. So it branches off into those two. And then once I buy a burger, I have the option of buying fries or rings or a salad. And then if I buy a veggie burger, I have the same options. I can buy fries. So there's one branch, rings, or a salad. Now, what this tree diagram allows us to do is see all the possible outcomes. We take any individual branch here, and if I follow this along here, I can go and find that red branch shows us one possible outcome. Or I could have a blue branch here, and the blue branch shows us another possible outcome. So we got burger and fries, burger and salad. And then we can continue to branch these off. Each of these if we had more levels, if there was, say, a drink, and maybe there was a dessert, we could branch off everything. But what you might notice is that this is already getting pretty big. I mean, I'm taking up a lot of space. If you start adding, say, 3 drink sizes, maybe there's 3 drink sizes and you pick, do you want a large, medium, or small drink? Well, now all of a sudden you have 3 coming off fries, 3 off rings, 3 off salad, 3 off fries, 3 off rings, 3 off salad. This can get pretty big pretty quick. So tree diagrams help us visualize when we're working with smaller things, but they do get difficult as we get bigger. Now, as for our sample space in set notation, what we have is we have the set equal to, and we'll have our curly bracket. And now we have burger and fries as one possibility. So BF. And that's not, let's focus. There we go. So burger and fries. Or we can have burger and rings. Or we can have a burger and salad. So that's these 3 possibilities. Or we could have the veggie burger and fries, the veggie burger and rings, and the veggie burger and salad. And then I'll close that set. So there's that sample space in set notation. So we just say what pairings we could have, and then we just simplified it by writing the first letter of the different pairings. Now, in the next part here, we have Spike telling the cook to make him whatever. So we want to know what the probability he will get a combo he doesn't like. So he doesn't like having salad with a veggie burger, or a burger with salad, because he wants, if he wanted a salad, he would get a veggie burger. And he doesn't like a veggie burger with fries because he finds the fries are too greasy when matched with the veggie burger. So what is the probability that he will get a combo he doesn't like? Well, the possible events here are either the burger with salad, and the other possible event is a veggie burger with fries. So there's 2 possible events of him getting something he doesn't like. There's 2 outcomes, and the sample space, there's a total of 6 items in that sample space. So the probability of him getting something he doesn't like is 2 over 6, which is 1/3, which is equal to 0.3333, repeating, or 33%. So there is the theoretical probability of him getting something he doesn't like. Now, with probability, the opposite of that is the probability of something is the complement of that, which is the probability of it not happening. So the probability of event A, the opposite is the probability of event A primed. So A primed, that little tick is not A to the power of 1. It means primed. It's the event not occurring. So our event A is what fits inside the circle, and then the rest of the sample space would be filled with event A prime. Both of those need to add up to 1. These are all the possibilities. The event we want, and then all the events that are not the one we want. So the probability of A and the plus probability of A primed is 1. So, looking at some examples, working with this kind of stuff. There are 10 books in a box, 3 romance, 2 sci-fi, and 5 mystery books. What is the probability of randomly picking a romance book? Well, there's 3 romance books in the box, so we can pick up to 3 options there. So the probability of picking a romance book is 3. The total sample space, all the books we can pick, there's 10 books to pick from. And so the probability of picking a romance book is equal to 3 over 10, which is 0.3 or 30%. Now, what is the probability of randomly not picking a romance book? Well, the probability of picking a romance book is 0.3. So if we want the probability of R primed, not picking a romance book, that is equal to 1 minus 0.3, which is equal to 0.7. So the probability of not picking a romance book is 0.7 or 70%. Now, last bit, odds. Odds compare the probability of something happening to something not happening using a ratio. So this is where we focus with part-to-part ratios. And we have the general format, which is odds in favor of an event happening compared to the odds against. So the odds in favor, the probability of an event, to the probability of the event primed, or not the event not happening. If the odds are, we say, and we would explicitly say the odds are against something, then we would say the not happening to happening. But in general, in most cases, this is what we're going to look at when we're giving odds: the event happening compared to the event not happening. So in the case of the example, a boxer is given a 60% chance of winning her next bout. What are the odds of her winning? Well, 60% to the odds of not winning then must be 40%. So the odds of winning are 60%, the odds of not winning are 40%. Now, we won't usually write ratios this way. What we would do is write this as a ratio in lowest terms. So that would 60 to 40% would be the same as 60 to 40, which is the same as 6 to 4, which is the same as 3 to 2. So the odds in favor of her winning are 3, and the odds against are 2. And oftentimes, if you were betting, this kind of, and it gets modified by bookies and things like that. But in general, if you were to bet and say, I bet she's going to win, for every $2 you bet, you will get 3. That's kind of how odds often work. But she's slightly more likely to win than she is to lose. About half as likely to win as she is to lose. Okay, so that's odds and theoretical probability.